Hello everyone and welcome back. Root Beer here looking at the 2016 Galois contest, and we are on the very last question, question number 4. The prime factorization of 45 is 3 to the power of 2, 5 to the power 1. In general, the prime factorization of an integer that's greater than or equal to 2 takes the form p1 to the a1, p2 to the a2, and so on, where p1, p2, all the way up to pk are different prime numbers, and a1, a2, and ak, these are positive integers. Okay, this is part of what's known as the unique factorization into primes, sometimes called the fundamental theorem of arithmetic. It's a really nice result, that all numbers greater than or equal to 2 can be uniquely written this way. Okay, so that's prime factorization. In case we didn't know it, they've got us up to speed. So given an input number, the Barbeau process outputs the number equal to, so n is our input, and I assume this is the decomposition of n. It's n times a1 over p1 plus a2 over p2 plus a3 over p, all the way up to ak over pk. Interesting. For example, given our input of 45, whose prime factorization we have up here, the Barbeau process outputs 45 times 2 over 3, because it's 3 to the 2, plus 1 over 5, because we have 5 to the 1 up here. And, oh, this is actually, if you multiply this out, you'll get n a1 over p1 plus n a2 over p2, and so on. But each of these will be integers, because p1 has to divide n. So you're always going to get an integer after this process. That's kind of cool. Maybe we're going to do sort of repeated Barbeau processes or something like that. Anyways, we get 45 times 2/3 plus 1/5, and this gives us 30 plus 9, 39. Okay. So that's the process. And we've got 3 parts here. Or sorry, 4 parts. 3 written parts, and then 1 light bulb. Given the input 126, what number does the Barbeau process output? Alright, so this is probably just a nice 1 mark, maybe 2 mark question. Basically, did you read and understand this brand new concept that we're giving you? Okay, so it's always a good idea to try the first part of the last question, be it Galois 4 or Euclid 10 or anything like that. Always try the A part question, because it's usually 1 or 2 quick marks. So what do we need to do? We need to figure out the prime factorization of 126. So I know there's a factor of 2, and that'll be 63. And so that'll be 7 and 9. So 126 is equal to 2 to the 1, 3 to the 2, and then 7 to the 1. Okay. Now, our Barbeau process says our output's going to be the same number, and then times 1 over 2, plus 2 over 3, plus 1 over 7. Okay. And if you want to, you can grab your calculator. I don't think I'm going to need it. 126 divided by 3 is going to be 42, times 2 should be 84. And then divide it by 7 should just be the 9 and the 2 again, so plus 18. Okay, 3 and 4 and 8 ends in a 5. Carry the 1, and we'll get 165. So that should be our answer, although we do have the prime factorization and the process written out, so, maybe we'll get 2 marks for this. Okay, and if not, at least we've shown we understand the process, so maybe 1 mark if I screwed up the calculation. Alright, now the next 3 parts require written explanations and shown calculations and cited results and those sorts of things. B part, determine all pairs PQ of different prime numbers so that the Barbeau process with input p squared q outputs 135. Okay. So P and Q are different primes, but we know the prime factorization. So we can see the Barbeau process. Pretty sure this is named after Ed Barbeau, who is very well known in math contest circles. he used to run sort of a mail-in. So you would mail him answers to a particular set of questions, and he would mark them and send them back to you. It was very nice. I think it was called the Olympiad Monthly. Anyways, so n times, and then it's going to be 2 over p, 1 over q. And now we can cancel out a p there, so we'll get 2pq plus p squared. And this needs to be equal to 135. So the first thing I notice is you can take out a factor of p. You get 2q plus p there. And so that tells me p has to be a factor of 135. Now what are the prime factors of 135? Well, you can take out a 5. And that'll be multiplied by 2 and shift the decimal place over 27. Oh, so we'll say only 3 and 5 are prime factors of 135. So either p is 3 or p is equal to 5. We just have two cases. They could both lead to q's. Neither of them could lead to q's, or maybe just one. Anything is possible. So we'll try p is equal to 3. What happens if p is equal to 3? So we'll get 3, and then 2q plus 3 is 135. So dividing 135 by 3, you'll get 2q plus 3 is equal to 45. Subtract 3. 2q will be equal to 42. Q is equal to 21, but that's not prime. Okay, so p equals 3 didn't lead to q being prime, so we had a bad sort of connection there, a bad assumption. That's fine. If p is 5, divide by 5, you'll get 2q plus 5 is 27. Subtract 5 from both sides, 2q is 22, and q will be equal to 11. So the only pair that'll work is 5, 11. Okay, and what number would that be? That would be 5 squared times 11, so that would be 275. Did they ask for the number, or did they just ask for p and q? Yeah, determine all pairs p and q. Okay. Alright, C part. Determine all triples, A, B, C, positive integers, so that the Barbeau process with input 2 to the A, 3 to the B, 5 to the C outputs 4 times 2 to the A, 3 to the B, 5 to the C. And we have to remember, these are exponents. They have to be positive integers. Okay. So I can't have A be 0 or anything like that. Okay, so, well, I know the factorization that we're going to be working with. So the Barbeau process outputs, it'll be n times a over 2 plus b over 3 plus c over 5. And we want this to be equal to 4 times n. Well, I guess I can just write 4n. Alright, they make it kind of clear that they're just looking for 4 times the original expression. So, dividing by n on both sides, a over 2 plus b over 3 plus c over 5 has to be equal to 4. Okay, so I need positive integers a, b, and c that do this. Now, I'm fairly certain that they're going to have to be multiples of these bottom numbers. So a is going to have to be an even number, b is going to have to be a multiple of 3. Otherwise, I just don't think it'll work. Although, how I'm going to show that exactly... Well, maybe we can get rid of the fractions. We can multiply by 2 times 3 times... We can multiply by 30 on both sides. And you'll get 15a, 10b, and 6c has to be 120. Although that seems a little less helpful. Although, okay, so I'm trying to show that A has to be a multiple of 2. That's sort of my hunch there. Because I don't think sort of a half plus 2/3 plus some number of fifths can equal an integer. It just doesn't work that way. It does work with some things, like a half plus a third plus a sixth. That equals an integer. But I think when they're all primes, you have a problem. That's my hunch. But let's see if we can follow this. So I guess if I rearrange to, say, 15a is 120, subtract the 10b, subtract the 6c, well, I can take out a factor of 2 there. So 2 divides 15a, and therefore 2 divides a, because 2 certainly doesn't divide 15, and it's a nice property of prime numbers that if a prime number divides a product, it divides at least one of the two factors of that product. So 2 divides a. I think the same sort of reasoning will tell me that 3 divides b. (15a) and 6c. So it's 340 minus 5a minus 2c. And c was over the 5, so this should be... Yeah, we can take out a factor of 5 there. Take out a factor of 5, you'll get 24, 3a, 2b. So similarly, we have 3 divides b and 5 divides c, because 3 does not divide 10, 5 does not divide 6. Otherwise, this wouldn't work. Okay, so, I don't know, let a be 2d, b be 3e, and c be 5f, I guess. So then we need d plus, 2d. So let's say 4 is equal to a over 2 plus b over 3 plus c over 5. And canceling things out, that's d plus e plus f. Now, a has to be greater, actually all of them have to be greater than 0. A, b, and c, they are positive. And so dividing them by 2, 3, or 4, that tells me d, e, and f are positive. And so how many ways can I take 3 numbers that are at least 1 and add them up to be 4? One of them is going to have to be 2 and the others will have to be 1. So either d is equal to 2, e is equal to 1, f is equal to 1. Or d is equal to 1, e is equal to 2, f is equal to 1. Or d is equal to 1, e is equal to 1, f is equal to 2. There's no other way about this. Okay. So our only possible triples are a, b, c are equal to, if d is 2, a is 2 times 2, so we'll be looking at 4, 3, 5. Otherwise, we get the 2. Now, e is 2, so we'll get 3 times that, so 6. And 5. Or 2, 3, and doubling that is 10. And we do just want the triples a, b, and c, right? Yes, we do. Okay. One thing we could do, I guess, we could double check this. You know, you got your calculator handy. You could pick one at random. Let's say, 2 to the 2, 3 to the 6, 5 to the 5, and do the Barbeau process to that. So if I multiply that by, well, let's see, it'll be 2 over 2. In fact, I don't even think I need the calculator. Yeah, the math says I'm going to get exactly what I wanted. 1 plus 2 plus 1. Okay? The only thing I would be worried about is there some other possible combination I'm missing? And no, because they have to be positive, and therefore D, E, and F have to be positive, they have to at least be 1. That accounts for 3 out of the 4. You're really just choosing one place to place that last 1. Okay? So those are our combinations. All 3 of them. All 3 triples. Okay, we got one more part, and then that's going to wrap up the whole contest for us, actually. Determine all integer values of n with 2 less than or equal to n less than or equal to 10, less than 10 to the 10, so that the Barbeau process with input n outputs 3n. Okay, so we almost saw this with the last one. We started with n, and you had 4n. So, well, how can we do 3n? So let's be general. Let's start with n is p1 to the a1, p2 to the a2, and so on. I don't know how many primes we're going to need. I would guess, if sort of the same reasoning holds that you have to have these factors, and you want it to equal to 3 instead of 4, I would guess at most you can have 3 prime factors. But let's not put any restrictions on there right away. In order to have the Barbeau process output 3n, we see that we need a1 over p1 plus a2 over p2 plus ak over pk to be equal to 3. Okay. Now I'm just going to notice this for later. Notice that each of my a's, so, a1, a2, I'm just going to write ai, is positive. Okay, it has to be positive, otherwise we're technically not including that thing in the count. Now, I claim, I'm just going to sort of do a generalization of the result that we had back here. I'm going to claim pi divides ai. That's what I claim for each I, for each of these possible numbers. So I claim that p1 divides a1, p2 divides a2, and so on. This is just a nice sort of short way to write that out. Okay, so I'm going to prove that. So notice if we multiply both sides by p1, p2, p3, just each of the primes together, we get, this is going to be an awkward expression, so you'll get a1, p2, p3, all the way up to pk, plus p1, a2, p3, all the way up to pk, and it'll just keep going on, all the way up to p1, p2, p3, and then the last one gets replaced with ak, and that needs to be equal to 3p1, actually, I'm going to add in a middle term here, this general ith term. So p1, p2, pi minus 1 times ai, pi plus 1, all the way down to pk. And now I'll write the last one. And all of this is equal to 3 p1, p2, all the way up to pk. Okay. Rearranging. And, if you're uncomfortable manipulating indices like this, you could just, I'm pretty sure we can make an argument before we do all this, that you're going to need at most 3 of these. But you should get comfortable with indices like this, even if it's a little hard to parse and understand as you're going along. But I'm just trying to be as general as I possibly can be. So rearranging, we see. So we'll keep the thing that doesn't have any PIs on this side. And that's only going to be one term. And so that's 3 P1. Actually, might it be easier to give this the name P? No, I don't think so. For a second I thought it just might cut down on some writing and stuff like that, but maybe it would work. So minus A1, P2, all the way up to PK, minus all the way down to P1, P2, all the way times to AK. AK is the last one. But we can take out a factor of PI from each of these. Which is, yes, boring to write out, but we are being exact. Well, actually, we don't even have to write it out. We can see PI divides the right, so must divide the left. Okay, so PI divides P1 all the way up to PI minus 1, AI, then the next one, all the way to PK, but the primes are distinct. So PI divides AI. Again, if you're someone who's uncomfortable with indices, just show it's true for P1 divides A1 and say the same thing works. I mean, we basically did that back here. We said similarly this works for B and C. I didn't write the full thing out. So, you're more than welcome to say it works for P1, A1. There's no reason it's not going to work for the other ones. But I've got this. So now I'm going to say let AI equal PI BI. And since AI is positive, we see each of the BIs is positive. Okay. 3 is equal to B1 plus B2 plus all the way up to BK. Okay. Since the BIs have to be positive and have to be positive integers, they're each at least 1. So 3 has to be greater than or equal to K, however many Ks that we use. So K is 1, 2, or 3, and that's how we can rule out there being, that you can't have 4 factors here. You can't have 4 different prime factors. Okay, so maybe we could do cases or something like that, or just talk about the different ways to write 3. 3 can be written as 3. In fact, so let's say this. If K is 1, 3 equals 3 is the only way to write. So B1 has to be equal to 3. So N is going to look like P1 to the 3P1. And for certain values of P1, this will be less than, 10 to the 10? Yeah, 10 to the 10. I don't know whether or not to list out the possibilities now or do it in a little bit. I suppose we can write them out with primes. 2 to the 6 will be fine. 3 to the 9 should be fine as well. Both those numbers are less than 10. 5 to the 15, however. So 5 to the 15 is bigger than 10 to the 10. I can see that on my calculator because 10 to the 10 should be 1 followed by 10 zeros, whereas 5 to the power 15 is 3 followed by a whole bunch of things. So 5 to the 15, just too big. It's just too big. So those two work from this pattern. What if k is equal to 2? Well, there's a couple ways to write out 3. Well, no, I guess you can't do 3 to the 3, 0. You have to do 2 plus 1. But you could do, 2, 1, and 1, 2. It depends on whether or not you consider P1 to have to be less than P2. No one said that at any point, so we don't have to assume that. So B1 is 2, B2 is 1, and N looks like P1 to the 2P1, P2 to the P2. What could we possibly have here? So P1 could be 2. We could have 2 to the 4, 3 to the 3. Pretty sure that'll work. We could have 2 to the 4, 5 to the 5. That might... Actually, let's take 10 to the 10 and divide it by 16 and see where we go. So, could we have 7 to the 7? Absolutely. So 2 to the 4, 7 to the 7. How about 11 to the 11 seems... Actually, 11 to the 11 is obviously too big. So that's it for those. But what if 3 is the one that's being doubled? So 3 to the 6, 2 to the 2. Yeah, that'll work. 3 to the 6, 5 to the 5. So 3 to the power of 6 is 729. Times 5 to the 5. Yeah, that works. 729 times 7 to the 7. Just grabbing the calculator. Yeah, that one seems to work as well. And of course, anything involving 11 to the 11 is way too big. Bigger than 10 to the 10. Okay, what else could we have? We could have 5 to the 10. 2 to the 2. 5 to the 10, 3 to the 3, maybe? So 5 to the power of 10 times 4. Yeah, that works. 5 to the power of 10 times 27 also works. I'm going to go out on a limb here and say 5 to the 10, 7 to the 7 is just a little too big. But I will double check it just to be thorough. I don't want to miss anything at the very end here. Yes, way too big. 7 to the 14. Can I even have that on its own? No, way too big. So that sort of runs out of our possibilities, but we've got 8 more. So do we want to count the number of cases, or do they want us to list them out? Determine all integer values of n. Well, here I'm actually writing them out. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 so far. Now, what if k is equal to 3? So I've got 3 prime factors. There's only one way to write 3 as a sum of 3 positive numbers, and that's 1 plus 1 plus 1. So n is p to the 1, p to the 1, p to the 2, p to the 2, p to the 3, p to the 3. What can we do there? Well, I'd try 2 to the 2, 3 to the 3, 5 to the 5. I strongly suspect this will work. And then we could probably... I can't use 11 to the 11 or any other bigger primes. So it's just a question of whether or not any of these is too big. I'm going to try 2 to the 2, 5 to the 5, 7 to the 7 first. Yeah, it's just barely too big, but that means I don't have to check this one here, the 3 to the 3, 1. Because it would be also way too big. But what about 2 to the 2, 3 to the 3, 7 to the 7? Is that too big? No, it's not. So this one here works. And the other one should work as well, but I'm a paranoid sort, so I will just double check it. So 4 times 27 times 5 to the power 5. Yeah, we're good to go. So it turns out there's 12 possibilities. I have them all written and highlighted in blue there. But I just, on the last page, let's put them all together. So 2 to the 6, 3 to the 9, 2 to the 4, 3 to the 3, 2 to the 4, 5 to the 5, 2 to the 4, 7 to the 7, 3 to the 3, 3 to the 3, 2 to the 2. Forgot about that one. Oh no, it wouldn't be 3 to the 3, it'd be 3 to the 6. 3 to the 6, 5 to the 5, 3 to the 6, 7 to the 7, I think worked. Yes, okay, good. And then we had 5 to the 10, and this worked for a couple of them, but not all of them. For example, 5 to the 10, 7 to the 7, just plain did not work. Okay, and then we've got the ones on our last page. We'll write them out again as well, I guess. So there's all 12 of our numbers. And these are the only ones that are less than 10 to the 10. So there we go. Nice little question, nice little answer, I think. Okay, and yeah, I think it's been a good Galois paper. I like it. If you're looking for more Galois, you can look forward to the 2015 or 2016, or sorry, we just did the 16, 2017. Those are nearby in terms of year. If you're trying to prep for your upcoming Galois, more recent years are always the better ones to do. If you're looking for a slightly harder, sort of similar paper, the grade 11 Hypatia might be up your alley. And if you're looking for grade 10 level, but maybe not so much writing, try the Cayley papers. You can look for the 2016 paper, or more recent Cayley papers is good too. But that's all from me, so thank you guys so much for watching. Feel free to like or subscribe, or leave a comment down below if you have different ways to do questions. And yeah, have yourself a wonderful day.